viewing transformations turns a 3D scene to a 2D image. In this video, I'll show you all the transformations and matrices behind this process. First, let's take a glance of the big picture. Camera transformation, perspective projection transformation, viewport transformation. Here we got an image. That's interesting. Let's dive into the first one, camera transformation. Let's give an example of that. The modeling is completed. Let's do the camera transformation. Our goal is to map these three vectors to the world XYZ vectors. An easy way to think about this process is that the camera is trying to be self-centric and want everything is labeled with its coordinates. I hit Ctrl A to select all the objects, including the camera, transform them until the position sits at the origin. Then try to rotate along the x-axis, y-axis, z-axis, until now the following conditions meet. First one is the origin of the camera sitting in the world origin. Second is the direction that the lens look at, or the gaze direction, should point to negative z direction. If negative z is counterintuitive, we can also think of the back of the camera points to the z direction. Third is the up direction that should align with y-axis. Then we know where's the x-axis. Now we know the result of a camera transformation. Let's decode the matrix of the camera transformation. First thing first, it's a composition of transformation. There is a translation and a rotation. Translation is easy. From the last video, we know that the fourth column denotes a translation. Suppose the camera position is these three values, then the translation matrix is simply negating the distance. Right, how about the rotation matrix? Write a matrix from this sequence is not easy. However, if you write the inverse, that will be much simpler. The inverse is just the transpose of that matrix. From this sequence, we know that the rotation matrix is just deconstructing the basis of the camera. So we put x, y, z bases to the columns, like so. Okay, if I want to go back, I can simply transpose this matrix. Then the camera position is aligned with our objective. In summary, a camera transformation is a matrix composition of translation and rotation. See this blue frustum? It's our viewing volume defined by the projection transformation. Everything inside gets rendered, while anything outside is clipped. Think of it as the camera's window into the 3D world. Basically, there are two kinds of projection transformation. One is called orthographic projection transformation. The other is called perspective projection transformation. We'll pick the hardest one. The big picture of this transformation is that we need to squeeze this frustum into a canonical cube, meaning all the x, y, z values within this cube are in the domain -1, 1. A perspective projection transformation matrix is composed by two matrices. One is perspective matrix, and the other is orthographic projection matrix. Let's unveil the perspective matrix. So the perspective matrix squish the frustum into a rectangular cuboid. This is the perspective matrix. The N denotes the distance from the camera to the near plane of the frustum. The F denotes the distance from the camera to the far plane of the frustum. To understand why the matrix is like this, reasoning is needed. I'll skip it here, but wrote a detailed blog post. Check it out in the comments. Another thing I would like to mention is that the N and F here are both negative, because we are looking to the negative z direction. For example, the near plane of my frustum is 320 to the origin. Far plane is 740. Then the matrix will be like this. Back to the video. We finished the perspective matrix. Now is the orthographic projection matrix. The orthographic projection turns a rectangular cuboid into a canonical cube. Let's unveil the orthographic projection matrix. Beside the N and F, we now have four more variables. Similar to N and F, the L denotes the position of the left plane relative to the center of the rectangular cuboid. The R denotes the right plane, the T denotes the top plane, the B denotes the bottom plane. Intuitively, the orthogonal of this matrix denotes scaling. The last column denotes a translation, so we can split this matrix into two matrices. One is translation and one is scaling. Let's see the translation first. The translation shifts the rectangular cuboid back to the origin. For example, in the z-axis, we have n plus f divided by 2 is the distance from the center to the origin. Negating this value moves it toward the origin. Next, we see the scaling matrix. The length of the edge of the canonical cube is 2. Therefore, the scaling matrix simply scales each side down to a length of 2. For example, r minus l is the length of our rectangular cuboid in the x-axis. Then 2 over r minus l scales the rectangular cuboid to a length of 2 in x-axis. Similarly, the second column scales the y direction. The third column scales the z direction. Eventually, the rectangular cuboid becomes a canonical cube. We can zoom in to see that. Now let's figure out the remaining variables of this matrix. We already know the value of n and f, but we still need to find LRTB, the left, right, top, and bottom boundaries of the view frustum. How do we calculate them? In perspective projection, there are two additional inputs. First one is field of view, FOV. This determines how wide or narrow the camera's view is. Some applications might use the term focal length, but it's essentially the same idea. Remember the view frustum before squishing? Then this is the FOV. Using the FOV and the value of n, we can calculate t using the trigonometry function. The second is aspect ratio. This is the ratio of the width to the height of your final image, like 16:9, 4:3, or 1:1. Normally, the face in the near plane and the far plane of the view frustum derives this ratio. Once we have t, we can find r, the right boundary, using the aspect ratio. Finally, the L, left boundary, and B, the bottom boundary, are just the negative values of t and r respectively. Here's a summary of the values. So we are given with FOV, aspect ratio, n and f, which could be seen as inputs. We can calculate TRBL, which could be seen as outputs. So this is the scaling part of the orthographic projection matrix. Combining with the translation part, we have this. And we finished the perspective projection matrix. Great job! We have just tackled the most challenging part, the perspective projection matrix. Now let's move on the last matrix and we are done. The viewport transformation just stretches to the size of our viewport, like 1920 to 1080 or something ultra-wide image like this. Therefore, the viewport transformation is like so. The first column scales the cube to the viewport size width in x-axis. The second column scales the cube to the height in y-axis. Suppose the height of my viewport is 4 pixels, then 4 over 2 is 2. Then the cube can scale twice bigger in y-axis. Same thing applies to the width. After scaling, we then translate this image, making the bottom left corner snaps to the 0,0 origin. Actually, this almost is the viewport transformation. But you might ask, what about the z value? Suppose the input is still a 4 vector, seen in the column picture. The z is not affected at all. Yes, in viewing transformation, we don't need a z value here. But eventually, the value can be used to determine like which object is behind one another. Excellent, you made it. That's all about the viewing transformations, and I have summarized for you in one table. Hope you enjoyed this video. Feel free to leave a comment if you have any questions. Subscribe for more videos about geometry. I'll see you the next time.